We just did a little demonstration and watched a little video of a hammer and a feather both falling at the same rate on the moon. In both of those things, that demonstration and video that we just watched, we learned that in the absence of air resistance, everything will fall at the same rate. A hammer and a feather in the absence of air resistance will fall at the same rate. A piece of paper and my keys in the absence of air resistance will fall at the same rate. Now, on Earth, that acceleration will be negative 9.81 meters per second squared. On the moon, it would be about negative 1.6 meters per second squared. Regardless of where you are, though, compare two objects, they'll both fall at the same rate regardless of their mass, whether it's 9.81 or 1.6 on the Earth or the moon. Now, anybody want to suggest to me why we say that acceleration of 9.81 is a negative value? Yep. Yeah, not because it's traveling downward per se, because it is possible to have an acceleration when you're moving downwards that's positive. It's moving downwards and speeding up in the downward direction. It's accelerating in the downward direction. Riley, if you were in an elevator and you were going down really, really fast, and then at the foot, you know, when you reach the bottom, when you're traveling in a fast-moving elevator, you reach the bottom floor, you feel that your stomach kind of going down into your feet, right? You feel really heavy for a brief moment. In that case, the acceleration is actually positive. You're moving downward, but slowing down. That's a positive acceleration. So moving downward, but speeding up, negative acceleration. Moving downward, but slowing down, that would be a positive acceleration. Now, what about objects that are rising up into the air? What if I take my piece of paper or my keys and throw it up? Well, when the paper comes back down, it's accelerating downward at negative 9.81 meters per second squared. But when it's moving upwards, the rate of acceleration is still negative 9.81. How come? Well, when it's falling, it speeds up in the negative direction. When it's rising, it slows down in the positive direction. So either way, again, speeding up in the negative direction or slowing down in the positive direction give you a negative acceleration. If you are slowing down in the negative direction or speeding up in the positive direction, the upward direction, then the acceleration would be positive. So what do we really have going on here? We want to solve problems involving objects that are falling or rising up into the air. How do we solve them? We got to understand that these problems are group B problems. It involves acceleration. Regardless of whether it's going up or going down, it's accelerating. Maybe decelerating, but still an acceleration. They're group B problems. The only difference between these group B problems and the group B problems that we've already done is that we know the acceleration in all of these. It's negative 9.81 meters per second squared on Earth or some other value on another planet. So in a sense, it's easier than the problems that we've already done because we use the same 5 equations, the same technique for solving them, but now we know in every single question the acceleration is negative 9.81 meters per second squared. We have an automatic given. Even if we're not told that in the question, we know that A is negative 9.81 meters per second squared. Example 1.17 on page 57 says, while cliff diving in Mexico, a diver throws a smooth round rock. They're saying it's a smooth round rock to suggest that there's no air resistance, basically. If it's rough, if it's wide, if it's a piece of paper, there might be air resistance. In all of these problems, by the way, we'll assume no air resistance because usually it's a close enough assumption to be a decent assumption. Throw it straight down with an initial speed of 4 meters per second. The rock takes 2.5 seconds to land in the water. How high is the cliff? All right, so what do we got here? It's a group B problem, right? Because the rock accelerates. What do we got here? We got an initial speed of 4 meters per second. You know what? I'm going to make that an initial velocity because it's thrown straight down. We know the direction. It's downwards. I'm going to make the initial velocity negative 4 meters per second. We know the time is 2.5 seconds. And if we read between the lines, we have one more given. One more given. What is it? Yep. Good. It's the acceleration. We know that it's negative 9.81 meters per second squared until it hits the water. We want to find the displacement. So I'm going to go back to my group B equations because it's the same problem now as we've solved for several days. Just that the acceleration is 9.81. Let's use this equation. VI is negative 4 times 2.5. Do you see how if I made VI positive 4, I would have gotten the wrong answer? Or if I made A positive 9.81, I would have got the wrong answer? Let's solve this now. Negative 4 times 2.5 gives me negative 10. We're going to say 0.5 times negative 9.81 times 2.5 squared. Negative 30.656. Add those up, we get negative 40.656 meters. We should round that to 3 digits. Okay, this is 3, this is 3. Final answer should be negative 40.7 meters. So the displacement of the rock is negative 40 meters. That means the height of the cliff is, technically it's positive 40 meters, the height, right? You made it negative, I'd accept that as an answer. Make sense? All right, here's your homework for tonight. Besides your velocity time quiz that is tomorrow, you have these 3 questions on page 58 to do. Remember, group B problems, acceleration negative 9.81 meters per second squared if you're on Earth, and if you're under the influence of just gravity. Otherwise, same problems as we were working on last week.